A clock on a mountain runs faster than one at sea level. Your phone quietly fixes that mismatch every time you get directions. Space and time are not flat backdrops, they are flexible. Here's the immediate takeaway: our intuition was built for small speeds. It fails in deep space or near extreme gravity. I want to show you how that weirdness actually makes sense. We will use real numbers and scenes you can picture. By the end, your brain will feel recalibrated, not confused. Strap in, because everyday space is stranger than science fiction. We start with a falling spacecraft that never hits the ground. That single idea unlocks almost everything else in this story. Picture a skateboarder in a giant bowl, circling without effort. Gravity makes a similar bowl in spacetime, around Earth's mass. A geodesic is the straightest possible path through curved spacetime. Orbits are objects following geodesics, constantly falling around the planet. That matters because it rewires what straight and force even mean. If you feel weight, you are being pushed off a geodesic. Free fall is actually straight motion, in the geometry space prefers. Mechanically, the ground supplies the push, your path wants to bend. Example: in real terms, the space station moves at 7.66 kilometers per second. Its altitude is about 420 kilometers, where air is very thin. At that speed, it falls toward Earth but misses continuously. After 90 minutes, it has circled once, returning above its track. No rocket is pushing during orbit, only tiny corrections for drag. Your intuition expects straight lines to stay straight in flat maps. Space near Earth is not flat, so straight paths look curved. Rule of thumb: if you drop something, it seeks a geodesic. Standing still fights that path, which feels like weight on feet. Airplanes follow arcs too, banking to trace efficient great circles. On a globe, great circles look curved, yet are shortest routes. Spacetime generalizes that idea, where mass reshapes what shortest means. Einstein replaced gravity's pull with geometry's guidance, which matches observations. Mercury's orbit shifts 43 arcseconds per century, exactly from curvature. That tiny number was the early smoking gun for relativity. So the picture is, falling straight can draw a graceful circle. You clap, then see lightning, then hear thunder in that order. Distance juggles the timing, because signals travel at finite speeds. Relativity pushes that everyday idea to its extreme logical limit. Simultaneity means whether two separated events count as happening together. Different observers can disagree, without anyone being wrong or tricked. This matters for navigation, coordination, and understanding cause versus effect. Mechanically, clocks tick slower when moving fast, relative to you. Also, lengths contract along the direction of motion, relative to you. Those effects combine so each observer's rulers and clocks stay consistent. Tiny test: imagine two lightning strikes hit opposite ends of a train. A person on the ground sees light reach them together. A rider moving right sees front lightning later, because motion matters. Neither is wrong, because at the same time depends on frame. At jet speeds, differences are minuscule, which hides the strangeness. At near light speed, differences explode, reshuffling cause and order. Cosmic rays show this daily, living longer because of time dilation. Muons born in the upper atmosphere reach ground, despite short lifetimes. From their view, the path contracts, so arrival becomes possible. From our view, their clocks slow, so decay takes longer. Both stories predict the same counts, which experiments confirm precisely. Particle labs measure time dilation to parts per billion every week. Satellite networks also depend on this, or they drift off course. Net result: simultaneity is local, and motion edits your time. Our senses prefer universal time, but the universe does not. Stand on a mountain peak and your time runs slightly faster. Dive into a valley and your time slows a hair. Gravitational time dilation means clocks tick differently at different altitudes. That matters for maps, money transfers, and scientific measurements worldwide. Here is how it works: gravity is curvature that affects clock rates. Lower in a gravitational well, light must climb, which taxes time. Equivalently, more potential energy above means less warping and faster ticks. On top, you also move slower than a satellite, reducing kinematic slowing. These contributions add and subtract, producing a small but crucial offset. Example: in real terms, a GPS satellite gains about 38 microseconds each day. Its onboard clock is adjusted slightly slower, so it matches ground. If engineers ignored that, your location would drift kilometers within minutes. Banks use timing too, so money would land in wrong accounts. Tiny test: tap a flashlight toward space, its color shifts red. Climbing light loses energy to gravity, which means longer wavelengths. Atomic clocks see that shift, even across a building's floors. In labs, moving a clock 30 centimeters changes its tick rate measurably. That is wild, but it is repeatable and reliable enough. So your phone, your paycheck, and rockets all trust flexible time. Bottom line, height and speed nudge your seconds, and technology compensates. That compensation is not cosmetic, it keeps the world synchronized. Once you see that, curvature stops being abstract and feels practical. Galaxies are not flying through a static arena, the arena stretches. Cosmic expansion means distances grow between clusters, even without motion. This matters for redshift, cosmic age, and our ultimate future. Here is the working picture. Space has a scale factor changing. Light stretches as that factor grows, increasing its wavelength and redness. Nearby, gravity binds galaxies, so local neighborhoods resist the expansion. Far away, expansion winds and recession speeds exceed light. That does not break relativity, because nothing outruns light locally. Example in real terms, galaxies 1 megaparsec apart recede near 70 kilometers per second. Double the distance and the recession speed doubles accordingly. Call that number the Hubble constant, set near 70. Overlay numbers help here because our brains like concrete scales. A galaxy at redshift 1 has its wavelength stretched by 2. Its light left when the universe was much younger. By arrival, the space between has grown, carrying it further. Distant supernovae appear dimmer than expected, revealing accelerated expansion. We attribute that to dark energy, a uniform pressure component. It behaves unlike matter, driving space to expand faster. One sentence recap: the map itself stretches and light stretches with it. That shift changes colors, distances, and how we read history. Look at a supernova remnant, tangled filaments drifting like smoke. Between those threads, space seems empty, but it never is. Quantum fields fill space, even when particles are absent. Vacuum means the lowest energy state, not actual nothingness. That matters because fluctuations nudge forces and even move plates. Here is how it works: fields jiggle, borrowing energy briefly. Pairs pop out, annihilate, and leave subtle measurable crumbs. Bring metal plates very close, and modes between get squeezed. Fewer modes means lower energy outside, so plates feel pushed. That push is the Casimir effect, measured many times. Example in real terms, micrometer gaps yield tens of nanonewtons. That tiny force still aligns with quantum predictions beautifully. Hawking radiation also springs from fields near event horizons. Pairs form, one falls, one escapes, stealing energy from black holes. We have not seen it directly, but analogs behave similarly. Lasers and fluids can mimic horizons, showing thermal emission. So even nothing contains structure, energy, and surprising consequences. What to remember: the vacuum is alive with fields, not empty. Your intuition expects silence there, but physics whispers everywhere. That whisper nudges matter, light, and even the fate of stars. Now zoom to a neutron star, a city-sized sphere of nuclei. Its magnetic field blasts beams, sweeping like a lighthouse across space. A pulsar is that rotating beacon, ticking with astonishing stability. This matters because nature built clocks we can read from Earth. Here is the trick: dense matter keeps time by inertia. Small, rigid, compact, it resists disturbances, holding a constant spin. Interstellar plasma delays pulses slightly, but patterns remain crisp. Example in real terms, millisecond pulsars tick hundreds of times each second. Some keep phase to about 10 to the minus 15. That rivals atomic clocks over months of observation, astonishingly. Spacecraft can navigate by pulsars, triangulating positions like celestial GPS. One demonstration nailed location within 300 kilometers across interplanetary space. We also weigh companions by tiny shifts in pulse arrival times. Gravity tugs change orbits, which modulate the ticking like music. The heaviest pulsars push toward two solar masses, stressing physics. Their densities exceed nuclear density, yet still hold firm. So timekeeping is not only for labs, the cosmos participates. Net result: nature's clocks confirm relativity and guide our journeys. That guidance feels alien at first, then wonderfully intuitive. Across a galaxy cluster, background galaxies appear smeared into pale arcs. Those arcs are not camera glitches. Spacetime itself bent their paths. Gravitational lensing is mass acting as an optics lens. It matters because it reveals invisible matter and distant structure. Here is how it works: mass curves geometry, so light follows curves. Multiple routes exist around massive clumps, arriving with different delays. Images duplicate, stretch, and form rings in rare perfect alignments. Example in real terms, Einstein rings can span 20 arcseconds across. Time delays between images can be days or even weeks. Comparing them lets us measure the universe's expansion rate. Weak lensing distorts shapes slightly across millions of background galaxies. Statistics reveal dark matter maps, tracing unseen scaffolding around clusters. Strong lensing makes dramatic arcs, usually around a massive central galaxy. Microlensing flickers betray planets, orbiting stars we cannot resolve. A 10% brightening might signal a Jupiter halfway across. Rule of thumb, curves in light reveal curves in space. We turn pretty swirls into numbers, then into mass maps. Those maps disagree with visible matter, demanding extra unseen mass. That is our strongest evidence for dark matter's existence. Bottom line, gravity draws pictures, and we have learned to read. Each arc is a postcard from the past, delayed by geometry. By timing them, we decode both distance and history together. There is a horizon around us, set by light and expansion. Beyond it, light has not had time to reach us. That boundary is the observable universe, not a physical wall. It matters because it limits questions we can answer. Here is the mechanism: the universe expanded while light was traveling. So distances now are larger than simple travel times suggest. Example in real terms, the radius is about 46 billion light years. The light began within 13.8 billion years of history. Space grew in between, stretching the separation dramatically. Black holes hold tighter horizons, one-way boundaries called event horizons. Cross that surface and return is impossible for any signal. From outside, infalling clocks appear to slow, never quite crossing. From inside, crossing is uneventful until tides become lethal. Hawking radiation slowly shrinks horizons over unimaginable timescales. A solar mass black hole evaporates near 10 to the 67 years. Supermassive ones would last far longer, essentially forever for us. Rule of thumb, boundaries appear when signals cannot compete with geometry. Cosmic microwave background forms another, a fog from early plasma. Before that, light scattered constantly, leaving a last glowing surface. So the boundary is, horizons mark limits of influence, not edges of existence. They remind us that knowledge is local, shaped by distance. Understanding those limits keeps our inferences honest and our maps faithful. We started with a mountain clock outrunning one at sea level. That tiny mismatch was the thread, and we pulled hard. Straight lines became orbits, time refused to be universal. Light traced curves, the map stretched, and horizons appeared. Example piled on example until your intuition loosened its grip. Net result, space behaves differently because spacetime is geometry, not stage. If this clicked, you now carry a better mental compass. Want more mind stretchers like this with real numbers and scenes? Tap subscribe so the next cosmic twist finds you early. Thanks for flying through spacetime with me, it was fun. Take a breath, then look up tonight and feel the curve.